Suppose the current IFT in an RL circuit is modeled by, so voltage over resistance times quantity 1 minus e to the negative RT over L. Okay. Find limit as R approaches 0 of IFT, assuming that voltage, time, and L are constant. Okay. Okay. So the idea here is a little background. So you have an RL circuit. That's a little switch. That's a little resistor. This here is, you know, I can do a better solenoid than that. I take pride in my inductors. There we go. And that last loop is not as good as the others. There we go. We'll call that our circuit here. So the idea is when you close the switch, you get a current flowing through the circuit. And the current will build up to some maximum point here, which will be V over R, which will be the max. And this will be time going this way. And I'm a big believer in the hydraulic analogy for circuits, for electrical circuits, because I think it gives kind of an intuitive feel for these things. So the hydraulic analogy would be that a battery is kind of like a pump. It pumps a fluid, water through it. A resistor is just kind of like a filter, as it provides an opposition to flow. And then an inductor, or a solenoid, a coil of wire, if you will, is a water wheel. So it looks something kind of like this. Come up, go back down, go over, have a little wheel, and then you have water flow through it. And when the water just starts off initially, the water wheel provides a lot of resistance. But once the water wheel gets spinning, then the water wheel provides very little resistance to flow. And that's what's being modeled here. But from the math point of view, there's like magic formula, work with it. And like, oh, okay. Which is what we're going to do. So we take the formula, take what they're given, and we do limit as R approaches 0. And I'll rewrite this a little bit. So V minus V, which is voltage, minus RT over L over R. Okay, so we look at this and we first see that, all right, when R goes to 0, we have 1 minus e to the 0 over 0, and that gives us the indeterminate form 0 over 0. And so what we think of when we see that is like, okay, L'Hopital's rule, because that's pretty much what you do every time you get an indeterminate form, either 0 over 0 or infinity over infinity. And so the idea with L'Hopital's rule is we take the derivative of the top, we take the derivative of the bottom, and then that will give us the same limit. Whoop. This is supposed to be I of t, current with respect to time, as R approaches 0. And so one of the things, some key points here is we're given I of t here, and normally when we do limits so far, we've only done limits with respect to the independent variable. But for this case, we're not taking the derivative with respect to independent variable, t in this case, x in most of what we do. We're doing it with respect to r, which is kind of like which is a constant here. But for this, we're going to treat everything except r as a constant. We're going to bring r down towards the towards 0. I'm going to do that using L'Hopital's rule. L'Hopital's rule is if you have an indeterminate form, take the derivative of the top, take the derivative of the bottom, and then when you have taken those new two derivatives, you take the limit again and see where that gets you. Another key point here is you're not taking a derivative of the whole equation. You're taking two separate derivatives, one at the top and one at the bottom. So we're not doing quotient rule, we're not doing product rule. I think we will do the chain rule just because that's the way the top works, but we will go from there and see. Ooh, blue. Okay. So L'Hopital's rule. And we take the derivative of voltage with respect to R, and we get 0 because it's a constant. Negative V. Yep. e to the negative RT. I'll clean up the board a little bit. We don't need this section up here. Oh, okay. Here we go. V e to the RT over L, and then we'll take the derivative of the interior, which in this case is negative RT over L, and so that will give us, or taking respect to R, so negative T over L, over derivative of R with respect to R, which is 1. So cancel those, and so now we take the limit as R approaches 0 of, so this goes to 0, and so this whole equation then goes to 1, and we're left with Vt over L. Okay? So our normal equation for a current, this is I, with respect to T, is you get kind of this, it works its way up towards some maximum value. So basically, when you think of it in terms of the water wheel starts spinning up until it reaches its max speed. But as resistance goes down to 0, what we get is Vt over L, which is kind of like this straight line. As V and L are constants, voltage and inductance are constants, and T just keeps getting bigger. And so what you get is this ever-expanding linear relationship. So what happens is you get this, you basically have this small section here, which is at the initial, and it extends it forever as the resistance drops down to 0. So in the water wheel analogy, when you close the switch and you put current through that circuit for the first time and your water wheel spins up, as resistance drops down to 0, that water wheel is going to keep spinning forever. Well, faster and faster and faster and faster. And it's going to have this relationship, voltage times time over inductance. And so look at our possible answers. It would be Vt over L. And that's the idea of when we have this equation for an LR circuit, RL circuit, and our resistance approaches 0. So you'll see these sort of questions a lot on AP exams. Not, probably not this specific one, but you'll see a lot of things that are taken from physics plugged into the equation or into the test, and kind of like, all right, here's this magic formula, and now you can work with it. Or you'll see a lot on free responses where they'll give you kind of a physics problem to work through, but they'll basically guide you through the steps. And it's not so much a physics problem as they're trying to work you through the math calculus part of it. And it can be a little bit cumbersome because it's hard to focus on the math when there's all this other physics stuff around. So it's good to have kind of an idea of what they're asking for, but try not to get too intimidated when they're like, all right, here's this formula, work with it. So that's how you approach this kind of problem. I will see you on the next one.